Microwave tubes, magnetrons, third part, series on microwave engineering, lecture number 4.33. Magnetrons are high power, high efficiency microwave oscillators, microwave tubes. Several varieties of magnetrons are there, but the type, the variety, the category that is in use at present is the one which is called cavity magnetron or cylindrical magnetron or conventional magnetron. It is a diode consisting of cathode and anode. Cathode is a solid cylindrical rod, and inside this rod exists certain number of heater coils. When they are connected to power supply, they generate heat, raising the temperature of the cathode rod. It ultimately leads to emission of electrons from the surface of the cathode. Cathode is surrounded by a cylindrical thick copper block. Inside this block there exists several cavities. Each cavity is a resonant circuit. These cavities are interconnected to each other through interaction region or interaction space. The space that exists in between cathode rod and anode block, that space is interaction space or interaction region. The electrons, after getting emitted, a part of them form into bunches. These bunches then deliver energy to the rotating RF field. This process raises the energy level of the RF field. It is then taken out for further processing, for further use from one of the cavities in the anode block with the help of a loop. In the present session, the focus is on the bunching process, which is key factor in the generation of signal by the magnetron oscillator. In addition to bunching, the focus is also on tuning mechanism that is there in magnetrons and also on efficiencies and operating characteristics of the devices, magnetrons. Now, let us move further to the core session to understand more about bunching, to understand more about tuning mechanism, to understand more about efficiencies pertaining to magnetrons, and also to understand more about the operating characteristics of magnetrons. Let us begin the session with bunching. In cavity magnetrons, the bunching of electrons is caused by a phenomena. This phenomena is called phase focusing effect. It is not at all difficult to understand this phenomena. Here we do understand this phenomena step by step. The cathode emitted electrons, they can be divided into two categories: favored, unfavored. Why favored electrons are all called favored? Why unfavored electrons are called unfavored? Reason is, favored are called favored because they participate in energy transfer from DC electric field to rotating RF field. Unfavored electrons are called as unfavored because they don't participate in the energy transfer from DC or static electric field to rotating RF field or wave that exists in the interaction region. Favored electrons, they come together, form into bunches, and then deliver energy, transfer their energy to the RF rotating wave, strengthening it, enhancing its amplitude. unfavored electrons, after getting emitted, they spend some amount of time, of course, a little time in the interaction space, and then they return back to the cathode rod. Favored electrons, of course, ultimately they get absorbed by the anode. Now, some more points regarding favored electrons and unfavored electrons. Favored electrons come together, forming into a wheel spoke bunch, spend more time and travel more distance in the interaction region, get decelerated by the RF field. This deceleration is actually the reason for the transfer of energy from electron bunch to RF field. Now these electrons get bent less, forming bunches, wheel spoke bunches, ultimately reaching and getting absorbed by the anode. Here bunches is missing. So this is what favored electrons behave in the interaction region. Notice their behavior is associated with deceleration by the RF field. The energy transfer is from bunch to RF field. On the other hand, behavior of unfavored electrons is exactly opposite to that of the favored ones. Unfavored electrons, they spend lesser time, travel smaller distances in the interaction region while getting accelerated by RF. Acceleration by RF means energy transfer is from RF into electrons. During this process, naturally, RF gets weakened, which is unwanted. We want the RF to be strengthened. So unfavored electrons, actually, they are involving in a process which is unwanted. Therefore, they are termed, they are called, they are labeled as unfavored electrons. They bend more, ultimately coming back and get absorbed by the cathode. The resultant wheel spoke bunches, these bunches, wheel spoke bunches, they are formed out of favored electrons. These bunches rotate counterclockwise direction with correct velocity, allowing continuous interchange of energy with RF fields. During this interchange, RF field receives much more from favored electrons than it gives to unfavored ones. Hence, there is a net transfer of energy from electrons to the field. Favored electrons give energy to the RF. Unfavored electrons take energy from the RF. But as favored electrons interact more amount of time, more amount of distance with RF than unfavored ones. On the whole, the transfer of energy into RF is more than transfer of energy from RF. It results in ultimately the strengthening of the RF field. Here is shown the bunch formation, the electron paths, and rotation of bunched electron clouds. Inside a traveling wave magnetron, when it is working in pi mode, all these things are illustrated here. First, pi mode. Operation is in pi mode. See, one pole is indicated with the plus polarity. Next pole is indicated with negative polarity. The phase difference between these two poles is pi. Not only these two poles, any consecutive poles. So this pole and this pole. This pole is negative polarity, this pole is positive polarity. Phase difference is pi. That's why this is pi mode of operation. As one is plus, one is minus, naturally the flux lines of the RF field, they appear originating from positive pole and terminating on a negative pole. Keeping this aspect in mind, flux lines denoting RF field, they are given here. They are shown in the diagram. Now, we consider two electrons, one electron P, another electron Q. In the absence of RF field, the electron, after getting emitted, it travels. Its path is shown its path is like this. It turns, it comes back to the cathode. This is the path in the absence of RF. In the presence of RF, its path gets altered. It travels like this, like this, like this, like this, like this. Notice while it is traveling in its path, it faces opposition to its movement from the RF field. As its movement is opposed by the RF field, energy transfer takes place from electron to the field. So the electron gets somewhat decelerated, but it continues traveling like this, like this, like this. Now, by the time the electron reaches to a position which is indicated by 2, it takes some time, of course, to travel from 1 to 2. Point 1 to point 2, it takes time. By the time things are arranged in such a way that the RF field also travels from one pole to another pole. It means the structure of the field that was existing at point when the electron is at point 1, same structure of the field comes into being with the electron when it is at 2. Therefore, at 2 also, the electron faces some opposition to its movement. Opposition means energy transfer from electron to field. So the electron gets somewhat decelerated, but it still continues moving. Ultimately, it reaches to point 3. By the time it is at point 3, in front of the third slot, the RF field also travels. The RF field which the electron faced when it is at point 1, same structure, same field reaches point 3 also. Again, here also, it faces opposition to its movement. Again, energy transfer from electron to the RF field. Ultimately, it travels further and reaches anode, gets absorbed there. So, the electron here, P, it is repeatedly giving energy to the RF field, strengthening it. Giving energy to RF field is a continuous process. The journey of the electron is continuous. The rotation of the field is continuous. The interaction between them is continuous. Acceleration by DC is continuous, and energy transfer to RF is also continuous. Of course, for the explanation's sake, we consider 3 points. But in reality, transfer is continuous. From DC to AC, transfer happens in a continuous manner. Come to another electron Q. This electron, in the absence of RF, it follows the path shown here with the dotted line and returns back to cathode. When RF is present, it takes lesser time because the electron is in such a position with respect to RF field that it gets accelerated by the RF. Acceleration by RF means energy transfer from RF to the electron. Electron gets more velocity. Velocity more means the impact of magnetic field or amount of magnetic force, it becomes more. Bending is more. Therefore, electron comes back quickly to the cathode. This is opposite to the behavior of electron P. Here energy transfer is to the RF field, it gets decelerated, bending becomes lesser and lesser, therefore it starts moving more and more towards anode. Of course, ultimately it reaches anode. Now one can understand easily why electron P is called favored electron, electron Q is called unfavored electron. All favored electrons, they come together and form into bunches like shown in figure. These bunches appear like spokes of a wheel, that's why they are called wheel spoke bunches. These bunches, they rotate, they keep on rotating. Of course, RF field also keep on rotating. While rotating, they interact with each other with a net energy transfer from electron bunch to RF field. This effect in which energy transfer takes place in magnetrons from electron bunches to RF field is called flywheel effect. Now, a few points on tuning. Tuning refers to changing or varying the operating frequency of the device. Frequency of a multi-cavity magnetron can be varied mechanically by changing capacitance or inductance of resonator, strap, auxiliary resonator coupled to the resonator system. We know what is resonator, we know what is strap, we know what is auxiliary resonator. By changing the capacitance or inductance of resonators or straps or auxiliary resonators, one can vary the frequency. Capacitance is varied by inserting conducting strips into the slots at high RF electric field points or bringing metallic rings called C rings close to the ends of the resonators at high RF electric field points or the insertion of conducting rings between straps or by bringing a conducting disc close to the straps. Inductance tuning is accomplished by inserting conducting rods lengthwise into the resonators at high RF magnetic regions or moving a conducting disc called L ring close to the ends of the resonators at high RF magnetic regions. These techniques offer moderate to good amount of tuning range. When extremely wide tuning ranges are required, usually split anode magnetrons, which operate as two gap traveling wave magnetrons, are used. So basically, changing the inductance, changing the capacitance of the resonators or straps is the technique that is used in tuning the device. There are certain drawbacks. All these tuning mechanisms, they suffer with certain drawbacks. The presence of undesired resonances which are associated with tuner structures and variation of unloaded resonator Q with tuning causes serious operational problems. Capacitance tuning, in addition, suffers with a limitation. Large tuning ranges result in small clearances between surfaces, carrying large RF potential differences, leading to the danger of sparking. While discussing about magnetrons, we come across three types of efficiencies. They are discussed here under efficiencies of magnetrons. What are they? One is electronic efficiency. It is the efficiency with which electrons transfer energy from the source of direct voltage to source of alternating voltage. Circuit efficiency is also there. It is the efficiency of energy transfer from the resonator to the load. Another efficiency is also used in the analysis of magnetrons, that is load efficiency. It is the product of electronic and circuit efficiencies. Electronic efficiency, circuit efficiency, load efficiency. These are the terms we encounter frequently in the study of magnetrons. Now, operating characteristics. The operating characteristics of magnetron can be indicated graphically in the form of a diagram. As the functioning of magnetrons depends upon large number of variables, the operating characteristics, they can be depicted in several different ways, giving rise to several different forms. So the basic aspect one has to keep in mind while trying to understand the behavior of the device is that its functioning depends upon large number of variables. Most important of such diagram forms are Hartree diagram, admittance diagram, and performance chart. The Hartree diagram shows the theoretical minimum anode voltage at which oscillation is possible for various modes. In the admittance diagram, the real and imaginary components of electronic and circuit admittance are plotted in rectangular coordinates. The importance of these two diagrams is limited to qualitative discussion only. In one form of admittance chart called load admittance form, the contours of constant power or efficiency and of constant frequency, they are plotted in coordinates of load resistance and load reactance. So in load admittance chart, load resistance, load reactance, these are coordinates and contours of constant power or efficiency and constant frequency. These contours, they are plotted. When polar coordinates are used, these diagrams are called Rieke diagrams. Its significance is it is possible to select load admittance to meet the requirements of high output power, high efficiency, and higher frequency stability. The load admittance chart is Rieke diagram when polar coordinates are used. Out of the three, the most useful chart with a lot of practical importance is performance chart. It denotes the contours of constant power output, constant efficiency, constant flux density, and occasionally constant frequency plotted on coordinates of direct anode voltage and direct anode current at specified load admittance. Performance chart is of greatest value for magnetrons because it shows in a single diagram the power output and efficiency capabilities of an oscillator and thus makes it possible the choice of a suitable operating point. Performance chart means direct anode voltage, direct anode current coordinates. Here are shown two diagrams A and B. In A, Rieke diagram, in B, performance chart. It is round in shape. Rieke diagram, it is a circular in shape because it is polar diagram. One can notice here 200 kilowatts, 215 kilowatts, 240 kilowatts, 265 kilowatts, etc. These are obviously constant power contours. Load here is shown VSWR over a horizontal axis 1.3, 1.6, 2.5, etc. One can also see somewhat vertical lines, broken long vertical lines with indication F0, F0 minus 1, F0 plus 1, etc. This F0, it seems it refers to frequency. If we move towards right side, it is reduction in frequency. Left side, it is increase in frequency. So contours of constant frequency. In B is shown direct anode current versus direct anode voltage. One can see contours of power 10 kilowatts, 20 kilowatts, 30, 40, 50, 60. These are all contours, continuous lines. One can also see the flux. These are somewhat straight, these lines, constant flux lines. One can also see the contours of constant frequency, 20%, 25%, 30%, 35%. So one can find three contours, power contours, flux contours, and efficiency contours. One can notice. Now, a few points on the noise characteristics of magnetrons. It is found the magnetrons generate more noise than predicted by short noise theory. While discussing the operation of the magnetron, it is told that some of the electrons, they come back and hit the cathode. And the electrons that hit the cathode, they are energetic electrons. Of course, some electrons hit anode also, but those electrons hitting anode, they are less energetic when compared to the electrons which hit the cathode. Anyway, the device involves electron hits. Each electron hit naturally, it creates, it becomes a source of noise. It is found magnetrons generate more noise than predicted by theory. Experimental investigations predicted this excessive noise is due to bombardment of cathode by the returning electrons, resulting in the generation of positive ions to neutralize the space charge in the interaction region and thus producing random variations in the space current. These variations in space current result in the modulation of the output or noise. Now, few points regarding specifications of these devices. These are high power microwave sources. used in radar transmitters and in linear particle accelerators. Of course, their use in radar, it is a past story, a past history. They are no more being used in radars. In earlier days, they were used. Cavity magnetrons cover the frequency range from several hundred megahertz to well above 80 gigahertz. The output that can be obtainable in pulsed operation is in the range of 1 megawatt. 1 megawatt of microwave power is a huge one. Electronic efficiencies range up to 71 to 72%. These are plus points. Giving higher powers, giving higher efficiencies, these are all positive aspects pertaining to the device. However, because of other reasons like noise and incoherency, they become unsuitable, they become unwanted in the design of sophisticated radar systems. As already mentioned, now they are confined to microwave cookers. These are some of the things which I want to share with you in the present session, in the third session, in the last session on magnetrons. Here, the main focus is on bunching, tuning, and operating characteristics of magnetrons. Enough for now. See you again in another session soon. Hope you have enjoyed the present session. Bye bye.